Good. Okay, thanks for bearing with me. So that prolonged your break a little bit. I'm glad to have you all here. This is a session that implicitly goes about coverages, as we have been discussing over the days now in many different setups. So it's a continuation, focusing specifically on gridded data. And so I called it Datacubes for multidimensional gridded data, but that's also what we have been discussing before. And so what I would like to show you is twofold. On the one hand, give an overview on coverages. Some of that you will have heard and you will know already. A few things might be new. I found in the discussion that a few things are maybe not as readily available as could be. So this would be sort of concretizing and detailing. On the other hand, I want to underpin that with concrete practical examples, discussing technology. We have some services online that would be used, and that is something that maybe makes it a little bit more colorful. But there's only one part of it, because I also would like to use the opportunity of this session to really have us talking, discussing, continuing, maybe refining discussions, and thereby contributing to the overall goal of this OGC/ESIP sprint of getting further with specifying how coverage analytics could work under OAPI. So let's go into that. Oh, by the way, and as always, please do interrupt me whenever there is a question, comment, or some request for clarification. So now, ideally, we can go forward. So this was a video which I wanted to show, but as audio doesn't work, let's skip that, save us some time. Just by way of background, this is where I'm coming from. Jacobs University is a university in the north of Germany, and I'm leading the large-scale scientific information systems research group there. So we essentially are database people, but with a focus on science and engineering data. So no business data and stuff like that, but science and engineering. Specifically, we research on all aspects of array services. There is a link here that gets you there. I will show you several links as we go ahead. Please feel free to approach me that I send you slides afterwards so that you can click these links, and maybe they will be uploaded somewhere, but I don't know yet. We'll see. Okay, so we have published on that. We have built the pioneer array database system Rasterman, and that has brought us into standardization, coverages in OGC and in ISO, but in ISO also fiddling with SQL. And by the way, a little bit of advertisement, both postdocs and PhD students, we are searching for complementing our team on various aspects, from theory to application. Okay, so this is what I would like to talk about, coverages and specifically Datacubes or raster data, gridded data. And that means talking about the data model and about the service model, which has been separated starting WCS2. And that is actually quite handy, but I will talk about that later on. And then underpin that, as I said, with technology example, also putting that into context with others and showing that live. Good. So as we have passed some time, let me skip this introduction part and just go over to this one, which is tentatively a shorter one. Much could be said, but we don't want to get lost in details. So coverage implementation schema, CIS, is the standard that is relevant for implementations. That's what the title says. And that we can put into context. And I've seen a lot of discussion going on here about features versus coverages. And that relates to the original definition, where the feature, okay, is a general geographic object, let's say, without going into the finesses, the details of that definition. And then coverage is a special feature. So technically speaking, a subtype. However, as we all know, they are technically rather different. So please don't think of that as a subtype in the sense of the strict subtyping in UML, in object-oriented languages or so. This is more like a conceptual model for humans. Technically, on a very abstract level, you could call a coverage some space-time varying phenomenon. Where does that come from? Well, I've pulled up here the highway networks of Germany, which is defined by vectors, of course. And if we go over highway A1, then this attribute A1 will remain the same over all the length of this polygon. And so we have one attribute value associated with a complete vector here. Coverages, and specifically now grid coverages, think of raster data. When you walk through that image within its extent, then obviously with every new location, you get a new pixel value. So actually the values that are associated change with space, and if you have time series, then also over time. This is what is meant by space-time varying phenomenon. This is a very general characterization, but not so handy in practice. So what I like to use actually is to explain coverages, saying that we have a couple of components. We have gridded data that are point data in the end, but points that are aligned in a very specific way. That specific way can be a regular grid, ortho images, for example, or they can be irregular, like swath data. Then we have point clouds, where the points don't want to adhere to any particular rule, so randomly distributed. Both are zero-dimensional. And then we have one-dimensional and two-dimensional and three-dimensional meshes, which resembles, in the end, feature sets again. And so altogether, we have 0, 1, 2, 3-dimensional stuff, the usual spatial objects. Okay, so this mini world, let's say, can be graphically described like this. We have the abstract coverage definition, and then we have the green part, which is the gridded part, which mainly is of interest today. This is like rings in a tree reflecting historical development. The first attempt was grid coverage. It's not encouraged to use today. It has a few shortcomings. Rectified grid coverage means we have, say, ortho images, and then referenceable grid coverage is all the rest of it. That was the classical distribution, following insight, following studying of this phenomenon of gridded coverage. Okay, with CIS 1.1, actually, we have managed to integrate all of that into one concept of general grid coverage, which also covers a few things that have not been there before. So if this green box is larger than the sum of the underlying boxes, then this actually reflects reality. There were a few cases which have not been considered earlier. Altogether, this is the world of Datacubes, if we want to use that term. And then we can go to the other side with the yellow boxes, where we have the multi-point coverages, so point clouds, curves, surfaces, solids, etc. Okay, so that is the abstract coverage concept, which has been set up by folks about 20 years ago. And we have subsequently tried to fill that with information structures and service definitions. In terms of specifications, we have the abstract one, OGC Abstract Topic 6, which is identical to ISO 19123. Now, you often will read that 19123 has been used as a basis for the implementation, and therefore it's standards conformant. Yes, and therefore it's interoperable. No. This is an abstract definition which defines concepts. It's not concrete enough to describe implementations. What does that mean? Well, you can interpret this, you can read it, understand it, and do an implementation, but nobody says that it will be interoperable with the definition of your neighbor. Just try it out. Such services typically come with their own client, and now try to use client A on server B. Typically that doesn't work because there is a lack of interoperability. Okay, Admittedly, in the original definition, that was not clear enough. In the 19123-1, which is currently under work, this will be formulated in a more concise way. In OGC speak, the standardization target of 19123-1 is not implementations, but other specifications. So other standards could relate and say, okay, we also want to use something like coverages, and here's the high-level definition for it. Okay, as this is obviously insufficient, but that's by design, we want it like that. It is complemented with a concrete definition, concrete in the sense that it gives direct implementation guidance and it leads to interoperability. Meaning, for example, we have conformance tests in place that check services down to the level of single pixels, whether they do the right thing. This, by the way, is a progress over WCS 1, the old deprecated version. There, the tests only looked into metadata. So a service that always delivers a black image would be perfectly compliant with WCS 1 as long as the metadata are good. In WCS 2, we look at both data and metadata compliance. Okay, and that is a coverage implementation schema. Both go together, and just to anticipate, this CIS is also an ISO standard meantime. It's 19123-2. That is in place since 2018. So we have a mirror of that abstract and concrete structuring in ISO world as well. Okay, now let's look at the structure of a coverage. This is something that you maybe have seen a lot. This is a simple way of squeezing into UML when somebody says a coverage is a function. So the domain set defines the input parameters to the function, so the locations, where do we have values, and the range set defines, well, the function result, what we can get back at that location. So like a mathematical function, domain, and range. Okay, technically we need a little bit more than that. We need to say, for example, what is the meaning of the range set values? We would like to carry that along. And so we have the range type, which defines what the meaning is. This is not just a technical data type like in a programming language. Don't think of integer versus float or so. This actually we have shamelessly stolen from SWE Common, from their data record definition, where they describe sensor values. And so you find valuable information like what are the null values, what is the accuracy. So a lot of things that are really essential for properly understanding the range values, the range set. Okay, we have a few more little details in the coverage box, which I'm ignoring here. And then something is missing. People wanted to have their own metadata, of course. So a bag has been added, which literally can contain anything. The coverage will not understand this, but it will duly transport it. And this way, we have the connection between the coverage and its application-specific metadata. Frankly speaking, what I would do is I wouldn't put too much into that bag. I would simply put a reference to a catalog. And the catalog would reference the coverage, say with a URL that gives access to exactly that coverage. And this way you have a bidirectional link. You don't duplicate metadata. You avoid all the pertaining consistency problems. And it's all handy and small. Because if it's any, think about that for a moment, it could become big. And if you want to get the coverage metadata, and somebody has put in a gigabyte of descriptional data, maybe this is not what you want to get, not what you are expecting. Okay, by the way, the domain set also can get pretty big. The classical view was, like with ortho images, we have regular data. It's all so neat and simple. So the domain set description will be very simple. Essentially a bounding box plus a few, plus resolution. But hey, we also deal with irregular stuff. And these irregular grids sometimes need much more data. Up to the effect that actually we can have domain sets which are larger than the range set. Sounds funny, but such cases exist. So if you have some very, very general irregular grids, then you could have to expect that the domain set can become large. That already destroys a little bit this old view of the range set is big and everything is small and neat and handy. I want to destroy something else. This view actually is only part of the picture. It allows nicely to explain main concepts, but don't see this as the data structure that is necessarily used in an implementation. There are many, many ways to implement that. And the first thing you would want to do is tiling internally. If you have massive multidimensional data, you want to split it into tiles. So this simple picture is already more complicated. But there's more to that. In particular, the sensor people have requested us to also support time series in the sense of coordinate value pairs. So we have a completely different structuring. The sensor emits a coordinate measurement, could be a time coordinate, could be a spatial temporal coordinate, plus the value, and the next one, and the next one. So actually what we get here is a sequence of coordinate value pairs, which is quite different from this here. And therefore, this is one of the things we are discussing currently in OAPI. Just basing everything on this picture is falling short. We might lose some interesting use cases and the structuring that is underneath. Okay, this on the side. But now let's get hands-on. So actually, this is the classical XML world. And if you want to have a coverage, you would see it like this. Actually, this is a little bit small. You know what? Let's go directly to the schema. And this is one link that I would like to show you. And if you want, you can just follow that on your PCs. So we go to schemas.opengis.net, drill down into CIS and go to 1.1. Then you don't find the schema directly, but you have to choose which you want. We go into GML here, and then you find examples specifically for coverages 1.1. So that gives you a large number of examples. And if you now go into the simple thing 2D regular, I can enlarge it here. And we see if we collapse everything, exactly that structure here, domain set, range set, range type. Okay, let's look into the domain set a little bit. We find a grid, some echo. We find a grid definition that actually says, let's read it from the back end. Axis labels is lat and long. So we know that the first axis is latitude and the second axis is longitude. We have an unambiguous description of the axis sequence, by the way. And then we go into the detail of each axis. Lat and long both are regular axes, so we can describe them by lower and upper bound and the resolution. And by the way, it also has a unit of measure level, so we know it's degrees and not meters, for example. So in this case, with the regular axis, it's really simple and compact. We underneath have then the Cartesian grid, so if you will, the array that is underlying in a storage structure, and that has axis labels ij. Oops, sorry, shouldn't click here. And you see the pixel definitions. When you go for geospatial subsetting, you're not so much interested in that, but sometimes you want to get stuff without coordinates, then you want to operate on this level. If you just do some image processing, say. Okay, so the next thing is, where are these defined actually? I mean, we have latitude, longitude, where do we get that from? GeoJSON says, okay, it's WGS84 anyway. Not everybody would agree to WGS84, and so we better indicate explicitly what the coordinate system is. OGC at some time has made a decision that we take URLs as the format to represent such URLs, such CRSs, and so we find the URL here going into OGC registry, into the EPSG branch, and there we pick for 326. So hooray, in this case, indeed, it is WGS84. Good, so we have everything we need. This is kind of a shorthand. If you want to know the concrete lat long definitions, then resolve that one. So I'm trying to copy here and go to the resolver, and you find more information than I can understand. Not being a geodetic guy or an expert in CRSs. So the link is there, the information is there for any system that wants to evaluate it. By the way, down there we use the same mechanism for what has been called the image CRS traditionally, and now we call it index CRS because it doesn't necessarily have to be an image. So we have an index 2D. Guess what? We also have an index 3D, index 4D. And that's what I want to show you next, actually. So let's take a four-dimensional example. Okay, now we know the structure already. We have our general grid here, and we have axes. Oh, wait a moment, we have more axes now. Lat, long, age, for height, and date. So actually we have a four-dimensional coverage here, so a four-dimensional data cube in this axis sequence. By the way, why don't we simply use the sequence of the regular axis items? Because some implementations tend to simply ignore the sequence. In particular, when you put XML into databases, they sometimes just ignore it. So the axis labels give us the indicative sequence of axes. Okay, now we find these axes again. Lat long we know already. H for height now is an irregular one. UOM label is meters, and you see the height levels indicated. I was too lazy to type more of them, so we have only 2 height levels, but I guess you see how we can extend that into any number of arbitrary positions, flight levels, for example. Okay, same thing for time. And here's something else. You have no idea how long we have been fighting for that in OGC, because the XML folks prefer numbers. And I said we need strings. Today that's okay. And also in CRSs, you can use such strings like the date indicators. And that allows us to flexibly define a data cube that has mixed axes, regular in X and Y, irregular in time and height. This is a case that has not been considered with earlier definitions. Good. So we have our 4D, our 4 axes. Now the question is, and what is the coordinate system for that? Good. That is up there, and now the ugly part comes. So this is the coordinate system, actually goes until here. That is the part of it. Let's parse it. So again, we go into OpenGIS.net in the definition branch, but now we find CRS compound. That is a mechanism actually that allows us to concatenate, to composite different coordinate systems into something larger. That mechanism, by the way, is also in ISO 19111-2. So that's nothing very special. And now we use that in a particular way. Our keys here in the parameter just give us numbers for sequencing. So the first part actually is we have our well-known EPSG thingy, but hey, it's 4979. Maybe it's not so common, at least to me it was not common. That is actually our good old WGS 84 plus height. So it's a 3D coordinate system that just adds height as a third axis. Good. And then we have another component, and that is time, which is something that OGC has done. EPSG doesn't want to maintain such kind of things. No problem. We bring it together, and we have a 4-dimensional coordinate system. So that allows you to pull together all the information. Again, you can look up the definition if you want. Everything is available, and including, just to reiterating, the axis sequence. Okay, so we have a complete definition of the domain set, everything we need to know. Okay, by the way, talking about that one, this is the range set. Then we have just simply values. Why do I show that? It's boring. Yes, but there is some ideas that we should fix coverage functionality to the range set. Now you see what the range set is. It's simply a sequence of numbers. You don't know the X versus Y distribution, you don't know the range type, you don't know where it's located in space and time. So actually, this is the really stupid part of it that doesn't know much. Therefore, we should really tie functionality to the coverage. The coverage is the intelligent beast that knows about itself. Okay, but in order to not get lost, this is something where you can look up lots of examples here in different situations in life. And you can do the same thing also in other coordinate systems. And you can do that in particular in codings. So if you don't like GML so much, maybe you prefer curly braces. And that is what the coverage would look like in JSON. Both is part of CIS. And so you can use both encodings, you can use them simultaneously, and the standard guarantees that they are consistent. You want to see examples? Okay, just go up in the hierarchy level and pick the JSON part. Then you find more examples here, the same ones actually as in GML, but now formulated in JSON. So, looks like that. And you can drill through the definitions as usual. This is still not your kind of thing. Okay, maybe you like RDF. If you like triples, okay, that continues approximately through the crust of the earth downwards. But hey, it's a concise definition. So we have a third way of doing that. Now, why would we want to do that? Already JSON, the mid-ocean people say, hey, stay away with JSON. We don't want to encode a climate model in JSON. Okay, but if you have something one-dimensional, a diagram, you want that. If you want to go directly into your browser, you want JSON. Same thing with RDF. So maybe you don't want to do number crunching, but you want to have a link into ontologies. And we had interesting discussions yesterday about that part, how we can achieve a seamless link and integration with the semantic web world. And here is one way of getting that. So an RDF client could look into the coverages from the RDF perspective without any special storage in the server. You don't need to store in RDF, that can be generated. And so actually we have all these formats available simultaneously. Okay, so once again, you can pick the definitions and the examples here on the OGC schema repository. Talking about the encoding now a little bit further in summary. So we have seen that we can use something like GML, JSON, RDF, and so on. And that is informationally complete in that it contains everything that's needed for a coverage. By the way, there is some inflation currently. We find others that also talk about coverages. My personal opinion on this is, in science, that's perfectly fine. In science, every thought can be thought, and thinking any thought is valid. So this is certainly interesting experiments, and I'm always interested in exchanging people. Why do you do it like this? And can we do something better? But from a standardization perspective, it's really detrimental. Because if I say coverage, what do I really mean? We may talk hours and hours about the same name and different things. So that's a little bit dangerous, and we should have convergence in the standards for the sake of interoperability and less confusion. Okay, end of personal opinion. So coming back technologically, so we have a format which is complete, but we don't always like it because it's not efficient. Okay, so the usual suspects are the binary formats. We want to use them. Good. So we have a string of pearls of formats that are supported for coverages. In other words, how is a coverage represented in that particular format? The start actually has done way back by Stefan up there, who has written the GeoTIFF specification. So mind you, not the specification of TIFF, but the specification of the mapping of coverages to TIFF. So this is actually relatively simple. You just say this is the coverages concept and this is the corresponding TIFF tag or so. And this schema we could carry over to many other formats. Don't be shy looking into these specifications. It's something, I guess, as an implementer, you will understand immediately. But now we have a problem. So we have the informationally complete inefficient formats, and we have the other formats which are binary and compact, but they cannot carry all information. Okay, one answer is, if the client selected JPEG 2000, they know what they do. and they just don't expect to get metadata because JPEG 2000 cannot carry this, and GeoTIFF also cannot carry all information. Okay, so if we are fine with receiving just some facets of the coverage, then this is exactly what you want. There are good reasons for that. But of course, we want it all, as always. So we need a way that we achieve efficiency and completeness of information. And the answer is container formats that do it in multiple parts. So the header would be something like domain set, range tab, type, and metadata. And then instead of the bits and pixels in ASCII, you would refer to a binary file that is part of the same coverage package. In CIS 1.0, only multi-part MIME was foreseen. In CIS 1.1, this has enhanced, and you can pretty much any container format you can use, like zip, for example, or the ESA safe format, and so on. The format, the mechanism is always the same. We have a canonical header, which is one of XML or JSON or RDF or something else that is complete. And then we have a number of files. By the way, this number of files can be used conveniently for a couple of things. First of all, tiling. You can transport a tiled coverage like this. But second, who says that only the range set is to be transported? We said actually at some time that the domain set can become big. Okay, so make the domain set a reference into another representation that is maybe more efficient. So you have many degrees of freedom to construct a container format as you like, and as long as you go by the rules, this will be perfect coverage. That is an interesting part for the discussion of the F parameter in OAPI, and that is something we still will work and we have to work on for getting such mechanics in. Okay, by the way, I don't know whether this is a concern for you. It was a long discussion in the WCS week, discrete versus continuous. Well, a continuous coverage has an infinite number of values. This we can't get into a computer anyway, unless we find a formula for it. That's unlikely for a satellite image. What we typically do is rather we have some control points or whatever you want to call it, and then an interpolation method attached. And that allows you to generate an infinite number of values because you can interpolate between the values stored. This is supported by the coverage concept by having a list of interpolations that are applicable. Now the coverage is a passive thing. It cannot do anything. It just can give a recommendation. So the client reading this can see that, okay, nearest neighbor and linear interpolation makes sense here. We cannot prevent them from doing, say, barycentric interpolation. Okay, but at least we provide the information. You also see that we have several possible interpolations. I mean, for general radiometric images, you want to allow linear, quadratic, maybe cubic interpolation. All of that makes sense. So very often you have more than one. In other cases, with discrete data, you have, I shouldn't use that word, with categorical data, you may have just one, and that is nearest neighbor interpolation. Okay, again, you see the concept of URLs, which is the common concept of OGC. It may be a little bit hard to read and type, but on the other hand, you have something that resolves, and you can always look up the definitions, and OGCNA can manage it. Okay, so that's it actually. We have now spent actually quite some time into the coverage data concept. We have 1.1 as the current standard, which is backwards compatible evolution. So 1.0 is not invalidated. GML-CAF is just the old name for it, the old abbreviation. And we have added a few things that turned out necessary and practically useful. And as I mentioned, CIS is also identical to 19.123-2. To be exact, that is the 1.0 version, and it's on our agenda for 2020 to also upgrade to CIS 1.1 in ISOWorld. Okay, and that's it. We have made a decision when we started WCS2 to separate data and service definition. And the advantage is that now actually coverages can be served by other services as well. So you can serve a coverage via web feature service, via SOS, via WPS, all of that. So you're not tied to WCS. Although I will want to argue next that WCS has particular functionality for this. With the screen sharing, it's pretty slow today. Coming here. Okay, here we stand. Good. So the idea of the service part, which I want to address next, is, of course, that we gather all these different data, and we know just how much of diversity we have here, and bring that together in a common concept, that is the coverage data model, that allows us then actually to offer common services. We don't want to have services for each individual data type, but we want to do visual inspection, mixing with other data, or just some machine-to-machine communication based on simple concepts that are applicable to all dimensions, to all data formats, and to all pixel semantics like temperature or radiometry or so. Actually, that relates nicely with SOS. For example, I'm just picking that one. Which is excellent for upstream data capturing. You can model pretty much any sensor that's possible and bring the data into a canonical structure. Do you remember? The range type in the coverage is exactly the SWE common definition. This is something we can exploit here because SOS generates something where the semantics is seamlessly transported into the downstream services where we have, among others, WCS and WCPS. So the coverage remembers its semantics. Okay, so coming to WCS, actually we, at that time, the modular design of specs came up and we were the guinea pigs trying that out. And after some time, there was a core, which is mandatory. Anything that wants to call itself a WCS has to do this. And that means give me a coverage, give me part of the coverage, and give it to me in my favorite format. That's all, nothing else. This is tentatively simple. It can be implemented by a gifted master student, I would say, as some thesis work. And so tentatively, the entry barrier for implementers has been kept low. By the way, subsetting is divided into trimming and slicing. Trimming retains the number of dimensions, so 2D cutout from a 2D map, and slicing reduces the number of dimensions. So if we see that on the right-hand side as a time series data cube, then we could extract a slice at a particular timestamp, or we could drill through the history and get the full history of a single pixel. Okay, the WCS extensions add further functionality facets, and these are optional. So whether an implementer wants to do that or not is their decision. That is actually good for agencies that pull out a request for products, because then they can say exactly what they require, and there can be an exact response that is backed by some conformance test that they hopefully have passed with OGC. And that gets into that big picture of the data and service model. It may seem a little bit complicated in the first place, but as we go through it, I guess and hope it will make sense. So the left pillar is the data part, which we have seen already. There's the coverage implementation schema at the heart, and then a string of pearls of format encodings that define how to represent coverages. Okay, and then we have the other pillar about the service model, where the WCS core is at the heart, which is mandatory. And then we have a string of pearls of service functionality. So WCST for inserting coverages, processing for doing analytics, range subsetting for extracting bands and variables, scaling, doing the obvious thing, CRS transformation, interpolation, and web query service finally. This functionality is defined in an abstract way, in the sense that you can use many ways to tell the server what to do. That is the so-called protocol bindings. So you can formulate your request in get KVP, in good old post XML, you can use SOAP, and as we are working on it, on API. So you have an abstract level where you can understand what scaling actually does without having to learn by heart what the encoding is. And we have very much worked on making the functionality available of all service parts under all protocol bindings. Okay, so I skip a little bit of here. That's more of an academic discussion. Let's get hands-on. Now, I apologize for taking the get KVP encoding because this is what runs best on my PowerPoint. And so we see here the get representation of a request that in the first place downloads some coverage. So request equals get coverage, the old thing, and then you provide the coverage ID. Good, maybe that is a few terabytes and we don't want to download that. So we do some trimming and slicing. That is done via the subset parameter, simply axis by axis. So longitude, we take an interval. Latitude, we can take an interval, so that is trimming. And in time, in this case, we do a slicing. We cut out a particular time slice. Do we know whether this coverage has a height axis? No, we don't. And we don't need to indicate that. If you want to access a 4-dimensional climate data set, okay, we would get all height levels. If it doesn't have height anyway in the first place, the same. So this syntax is really agnostic of all the axes that are not of interest. We only address those axes which we want to touch upon. Okay, and then getting the favorite format. This is the same thing as with the F parameter in OAPI. It's just that it's spelled out format. And we use the MIME type identifier as something that is also settled by some standard committee so that we have a unique identifier. And that's it. So WCS core is essentially one slide. Let me go through a few selected extensions just to show you the mechanisms behind. Very often, we can just add further parameters and that unleashes further functionality. So range subsetting, for example, I want to get some bands or variables, say RGB from a hyperspectral image. The parameter name here is range subset, and we can indicate one or more bands. We can do that in arbitrary sequence. We can have intervals of bands. Think of ALI Hyperion, where you have hundreds of bands. And this way, you do another subsetting, I'm saying that cautiously, on the range records. Okay, so it's still the get coverage request, but with additional parameters. Same thing with the CRS, which is also a discussion that is in more or less in full swing in OAPI. And in this case, we actually have added two parameters. The one thing is output CRS. I want to get this coverage, but I don't want to get it in WGS 84. I want to get it, say, in ETRS 89. Okay, so the server translates that for me and delivers that to me in this output CRS. But there's more to it. Maybe my bounding box is in a different coordinate system. This is governed by the subsetting CRS parameter, where I can indicate another parameter, another CRS for the bounding box parameters as they're interpreted. So actually, if somebody implements the CRS extension, we have a few ways to jump between the coordinate systems. Remember, these CRS definitions, the normative ones, are given as URLs by OGC. You could define your own ones, but then you are living in a bubble. Okay, here is another example now where we could not and did not want to extend the get coverage because it's about, say, put in HTTP sense. WCST allows you over the web to modify your service by uploading new coverages, that is insert coverage, by deleting them, or by updating an existing coverage. And with update, it's particularly important that we have partial replacement. That's actually the common case. If you build up a data cube, you have thousands of images or so, you bring it in one by one by one. So you would use update coverage for that. That can be as simple as that. See, we have a new request type here, insert coverage, and we give reference to some netcdf file, which the server fetches. Of course, the server must have access to this. And then we generate some object, and we provide a new generated use ID. If you know an identifier for the coverage, then you can pass that one. It has to be unique, of course. If you don't know what could be a unique identifier, just say use ID equals new. And that's it for generating a new coverage, as simple as that. We have put much emphasis on the mechanics that what you get back from a get coverage is the same as an insert coverage expects. So you can easily extract from server A and insert into server B. So you can easily transport coverages. Okay, so that means generating new request types. And now, many people are so sure that that had to come at some time. My favorite one, of course, is WCPS, the processing extension of WCS. This also defines a new request type, but wait a moment. First of all, what are we talking about here? WCPS is in the end a Datacube analytics language that is aware of the semantics of space and time. So this you see with a subsetting that is here in the compact form. It knows about latitude, longitude, and time, etc. Can handle regular and irregular grids. And just to give you a flavor of it, the yellow box first iterates over 3 coverages, M1, 2, and 3. And for each one, it performs the return statement, which says, give me the difference between red and near infrared, encode that in TIFF. So the result of that request would be 3 TIFF images. Okay, you can also do filtering, not just processing, and that would introduce the where clause. You can introduce a condition, and you see this is not a condition on the metadata, but this is a condition on the data. So you really work on the pixels, and you filter on server side, so what you don't want never leaves the server, and you don't have to wait for that. So that is the principle of it. We have something that looks close to xquery and xpath because we have lots of XML metadata around. Okay, and so you send such a query, a string, to the server, and you get back a response set. That's it. What can we do with that? For example, we can do a fusion of elevation data and images, and you get this rendered 3D terrain draping in the background through a WCPS request, which operates on 2 coverages, so it does a data fusion here. You can emulate a web map service by saying, I take 4 coverages, I overlay them, I color binary layers, I do some terrain coloring on the DEM, stuff like that. That's actually the way we implement WMS internally. Okay, wait a moment. I hear you think. We have a WPS. How does that relate? Can also work on coverages, as I said, but there is a fundamental difference in the approach. With WCPS, we have a query where syntax and semantics is defined in the standard. 2 different servers will always have the same interpretation. Otherwise, they are buggy. In WPS, actually, the semantics is in human readable text. If you want to find out what this process really does, essentially you have to look into title and abstract, and that is nothing a machine can interpret. So you always rely on that this process really creates a buffer around a polygon. So this we could call syntactic interoperability because the format parameters, the input parameters are specified, but not what happens inside. Is that a criticism? No. Actually, it's just for different use cases. So WPS works with predefined processes, maybe code that you already have and that you want to bring to the web. WCPS does ad hoc analytics. You send a query and you get a result. And if your algorithms are mighty complicated or you have the code already, then you will want to go for WPS, not for WCPS. If you want to be flexible, any query, anytime, you may prefer WCPS. And hey, if it's just about simple data access, then use WCS. So we have, say, a continuum, a portfolio of services where you can pick what you want, and via the coverage, the CIS, this all works together. Okay, so that was some walk through the requests, the functionality that WCS offers. Now let's come to that final string of pearls and the protocol bindings. So we always have used GetKVP in the examples, but actually, as I said, we have several of them available. We also tried it with REST early on. You see that this was from 2012, but as usual, you say REST and a discussion explodes. And so we didn't get to a result. Now with the next approach, OAPI, I'm more confident that we will have something that gets adopted and works. Okay, so coming to that one, you see that actually it fits in into this world. And so the good news is, if we manage to do it, yes, let me say that. If we manage to do it in a good way, then actually we will not invalidate existing services, but we will just add a new facet. You like OAPI? Excellent. Okay, then use the OAPI protocol binding and get the functionality. You like SOAP because you have, say, legacy code? Okay, stick with SOAP, same functionality. So this is something that represents somehow the current state. The current state is in flux. And also during these days, we've been discussing a lot on the concepts, just to show you the flavor. And once again, if the activists here have something to say, please chime in. So we have the API path that goes down into collections. And the collection ID gives you the object in this case, which we want to see as a coverage. So you see, I'm trying to interpret the URL now. So the coverage identifier is actually the collection ID, something that NetCDF guys found confusing. So we need to explain that better. And as it stands currently, /all gives you the complete coverage. Why that? Because there was a decision that /coverage, without anything else, gives you the coverage metadata. Okay. It's one way of doing it. You could also think about delivering the coverage when you say coverage, but currently we have a /all if you really want to get the coverage. Then we have qualifiers for the particular components, domain set, range type, metadata, range set. And description actually is a shorthand for the old describe coverage request that bundles domain set, range type, metadata. So effectively anything except the range set you would get back. This is the current state, and this is also something that is, I think it's fair to say, under discussion. Okay, one thing actually where we also have a discussion over the feature guys, subsetting in n dimensions works a little bit different. So the OAPI common style, which is here shown in the 2D example, lists some coordinates. Question to you, which is lat, which is long? Yeah. Okay. In my humble opinion, major source of errors. In the coverages, we have the subset approach where you go axis by axis, and so you name the axis that you are subsetting individually. So for example, doing our good old thing about the time slice would be subset equals time and so on. And doing trimming and slicing would be the same thing. You see that it follows the question mark, so it's a parameter, it's a query parameter. Why don't we put that into the path? Well, because the path is a linear sequence, but the dimensions are all on the same level. There is no preference. You cannot say this is the first, this is always the second, this is always the third axis. This is individual per coverage. And hey, in my request, maybe I don't want to do subsetting in space, maybe I don't want to do subsetting in time. So this multidimensionality just doesn't fit into 1D, and therefore we need that subset mechanism. Okay, coming to that last part. If we wanted to queries, we would likely go to collection level. We would operate on collections. And so one idea that has emerged here during the sprint is that we have a keyword WCPS, which says this is a WCPS query. And then you simply pass the query string as a parameter. By choosing WCPS as the parameter name, we make way that we can also have other query languages like CQL or feature filter encoding. So we can support different query languages in an easy manner. Okay, there is a demo actually that we have done for the sprint and during the sprint. And I'm trying now to do that. Edit hyperlink, copy hyperlink. Hello? Interesting. It's coming, it's faster on your screen than on mine. Fancy. Okay. So here is the Google document coming that has been used as a scratchpad for describing the summaries. And as it's loading, yeah. So for those of you who have access to this, again, you can do that simultaneously. Hooray. So now here we go. And I'm not so familiar with that one. View should do it, present. And then the link should work. Should. Hello? Okay, finally. Good. So we send that link. And what's that? I've never seen that before, white label error page. But I know what the issue is. Yes. Because we initially had a wrong keyword here, coverages instead of collections. Okay, so we get back that PNG image. And now let's do the same thing with the processing part. View in presentation mode. And some age later, we come to the next one, where we actually have a query that goes into the Sentinel-2 image, computes NDVI on some subset and returns that as a PNG, sorry, as a JPEG image in this case. Okay, and here it comes back. So next one shows aggregation. Why do I have to go back to presentation mode every time? Good. And sorry? Maybe I should say open a new tab. Yeah, it's all funny. You will notice there is not much difference to the previous query. Actually, the encode part has been replaced by average. So we do an aggregation now, and we don't need to encode an aggregation. We just get back an ASCII number. And now I'm trying a new trick. No, it didn't help. But we get, hooray, a value back. Not very impressive, but it shows how aggregation works. So what you also can do is go into the copy link URL. We have put such an open API definition file online, and then you put that into Swagger just to demonstrate that this works too. So no, come on, import URL. And the winner is okay. I could do that. I have it locally. Maybe works faster. Okay, now we get the collections and we can run the request from here. Where's my execute? Try it out, and then I get an execute, and I get back the image that we have seen before. So that is underlining we have some functionality that we have seen before with WCS because it simply makes sense. We want to do subsetting. We want to do analytics, which was in the title. So that is what we just do in a different syntax, but it's not quite that. So it's not directly a one-to-one translation. So there is still enough questions in it, how to deal with various differences that are induced by the different path notation and path mechanics, as opposed to the other bindings. So there is still some work to be done. But that was the part of having the core and extensions functionality presented, in particular the WCPS part, and that shows how query languages could nicely integrate with OAPI and with other OGC mechanics. The whole thing is not just paperwork that has been adopted back in 2012. We see lots of implementations of that. And if you want to follow that, I never can remember URLs. So I need to click through. And the winner is, so that is a wiki page where you find information, for example, about known implementations. The message here is twofold. Number one, you find the usual suspects implementing WCS. So there's a broad basis of both open source and commercial tools. And the second message is, if you know of anything not listed here, please let me know. I would love to add your product, your tool on that list. And that certainly gives you extra visibility. So please let me know about it if you have something. And if you want to have a link here, then okay, tell me as well. So I will link to your homepage. Good. So then recently somebody said, oh, but this is so complex. We have made experiments, not tentatively, not planned, and people who have not been exposed to OGC standards before, actually, the statement of Stefan is immediately feel at home with these standards. So it seems to work, and it does work. It is operating on multi-petabyte holdings, and it is doing actually data fusion queries. And that is what I would like to show you live right now, just to underline that, yes, these coverage services make sense. So this was a project where we extended the German Sentinel Hub code.de with Datacube, let's call it a Datacube front end. And I want to show you just one of those. I don't know whether links are large enough that you can see them and can copy if you want. I want to show you just one thing. While we are talking, now actually we are doing a federated query. That is the query here, WCPS, where we actually generate a PNG image that consists of red, green, blue, the visible bands of Sentinel-2, of a Sentinel-2 scene. And in the alpha channel, we put elevation information, and then we get something in WebGL here in the browser. Just to show you that this is really live and we can vary it, let me establish a sunset scenario. And while that is loading, so here is our sunset. So Sentinel-2 is in the RGB channels, and in the alpha channel, we actually find a digital elevation model that is provided by Claudio, which is a German geoservice provider. So actually what's running here is a public-private partnership. But with Code.de, we can do more. Can we? Yes. I said it's a federation, so ad hoc resolution of requests. Here's something that we also sent to Code.de, another WCPS request that is using total precipitation, so climate data, and Landsat 8 data. Let's see what happens. We see the path of our query here as it walks over from Bethesda to Code.de, and then a little bit onwards. But before explaining that, let's look at the results, which we see here displayed in NASA Whirlwind. So what has happened here? This is where Code.de sits, and they actually had to fork a subquery to Creodias to another data center because they don't have all the data. So this is a federated query. Actually, we could also send it to Cloudflare, to our Polish friends, and now they in turn have to ask Code.de for help. In the query, you see nothing about the location, and the processing actually is optimized between those servers, so they talk to each other to find the most efficient way of doing it. Here is another example of what has been done in Taiwan. This is vegetation expectation, so forecast, and we send that to Taichung, where the data center sits. They also have to ask for Code.de data now. And when the result comes back across the planet, then we use again NASA Whirlwind to show the NDVI forecast for the northwestern territory of Taiwan. And again, we could send that to the other service. They all do it transparently, but okay, that's boring. We have seen that before. Okay. Now trying to find my virtual machine again. Okay, it's coming back to me finally. So just a quick thing. So I won't go through these, but just a few selected items. Did I say that we come from a database background? So actually, this is an array database system that operates on queries, and the queries happen to work on multidimensional arrays. Actually, with the work that has first been published in 1992, we have coined array databases and actionable Datacubes, and that is something that I showed you is in action. And internally, we use a query language that looks like that because geo is just one particular application. This is domain agnostic. Without going through the details, we can do that offline later on, but at some time we really want to have lunch. You can go up to linear algebra operations. Here we see matrix multiplication, for example. But again, I don't want to explain the language, which, by the way, has the same structure as WCPS. Internally, we map WCPS, we translate it into such queries. And that, meantime, is part of the ISO SQL standard. So part 15 has been published in summer last year, and that adds MDA, multidimensional arrays, to SQL. Looks like this. You can define something that is of type MD array, multidimensional array, and then you can use processing directives in the select part and in the where part. That is domain agnostic. It doesn't know about space-time semantics. And something that was unexpected in the beginning, for the first time, we can combine red and green queries in one single query. Green are metadata queries. Red are data queries. So actually, where we have these different silos today, in future we will have an integrated information space where data and metadata distinction doesn't matter so much, doesn't guide architectural decisions, at least not for the user. We can also add in user-defined functions, as it's called in databases, so external code that can be invoked from within the query language. But again, I'm cutting short and just showing the architecture, where we have the Rasterman server workhorse in the center. Pixels can be stored in a database like PostgreSQL, or in our own storage manager, is about 2 times faster than PostgreSQL. And then the big data centers came and said, forget about it. We are not going to copy petabytes into a database. And therefore, we needed to learn how to deal with existing archives. And today you just tell us the conventions and then we register instead of import data. And query processing is just the same. I showed you a demonstration of the federation part. Actually, we do it that way that we analyze each incoming queries. I mean, we know the semantics of it. So we find out that the yellow part we can do because we have on our know the yellow data set A, not so the orange part. But we know a friend who has these data. So the orange part we cut out and send as a separate query to our friend in the cloud. And this is how we do cloud parallelization. Of course, we also do multi-core parallelization, but that's a different story. Okay, with the same principle, we also can go to other data centers. So the blue part would be sent to the blue house for processing where the data sit, and only the result comes back and gets integrated. This is what you have seen live with Taiwan and with Germany and Poland. We have a project where we actually have implanted Rasterman on a satellite, on a CubeSat. And so this becomes a data analytics engine that also responds to queries. So it takes an image and then you send up a query and you just can get back the result, which typically is much smaller and hence much faster. I can show you an example for that because we were doing experiments here. And let's see, this is a race that we are watching. Some people say a service must be as simple as ever possible in order to be fast. So what's the simplest thing? Give me that file. A web server giving me the file. That's like with WMTS, for example. Okay, the left-hand side is a false color image that has been delivered by an Apache web server as the file stored, which is a few megabytes on disk. On the right-hand side, we previously have imported the image into Rasterman, and we have sent a query now that computes the NDVI and does a thresholding. Wait a moment, that should be slower. We have done processing. Now the processing in Rasterman is so fast that you don't realize it. What you realize, however, is data transport. So let's look at it again. On the left-hand side, each pixel has 24 bits. On the right-hand side, each pixel has 1 bit. And looking at that image, hey, that compresses nicely. So effectively, with a suitable data format encoding, on the right-hand side, we talk about kilobytes, and on the left-hand side, we talk about megabytes. And this explains why that is slower. So my dogma is exactly the inverse. The more intelligent a service is, the better it can fulfill my request. And that means better service quality, and that means more speed. Okay, I just had to show you that because that's also an ongoing discussion. Okay, so that is how we do distributed processing. We do that by analyzing the queries. And a lot more stuff inside, but that's not our topic. Actually, oh, come on. The screen is getting so slow, and I'm still annoyed by the fact that you see the image faster than I see it on my own screen. Okay, we have done this, of course, with satellite and with climate data. You have seen that also with geophysical data. And just to find out whether the coverage concepts work, we have started doing that for planetary science. So this is planetserver.eu, is a portal for Mars, Moon, and Vesta currently, but also cosmological simulations and human brain imaging and the like. And so you sense already I'm somehow intrigued by the idea of query languages, giving us the opportunity of any query anytime. And so I cannot resist bringing up that one to provoke a little bit. These query languages like WCPS and SQL are safe in evaluation, as it's called in databases. So a class of denial of service attacks is simply not possible by design. Whereas if you ship Python code, okay, will be interesting what you get. A denial of service attack in Python you can write in 2 lines of code. But that was just an inset. And actually, I would like to stop here and see. I haven't heard any injections so far. So cleaning up here and just seeing where do we stand? What do you think about it? Any comments? Any insights you would like to share? I'm just cleaning up here.
Just a small technical question.
Yes.
So what happens if you run a coverages request that takes more than like 5 minutes and HTTP times out? Are there any provisions in the standard for asynchronous?
What the current specs do is synchronous transport. So you would wait more than 5 minutes. So it would make sense to have asynchronous processing as well. I was looking around. First, I thought WPS is the optimal carrier for that. So we would just piggyback with WPS. But after some discussion with OAB and the OGC Architectural Board and the WPS guys, it turned out, no, that's not the right thing. What seems to be a good approach is the pub/sub specification of OGC. That is something that is waiting to be coupled. We would need to make experiments and see whether it works. Would be a typical case for test beds, but they had different interests. So that should be promising. But it's currently not in any specification. It's not yet a WCS extension.
So why piggyback on WPS is not?
Well, because WPS knows about processes, and you could just see a request, a get coverage request or a WCPS request as a process. It can be defined easily. We have done that. So experimentally, we have shown that it works. But then they said, no, that's not a good thing for defining the asynchronicity, because you have to do a lot more things that you actually don't want in our context, that you don't need from WPS. So you have an extra burden. You see that I'm phrasing that carefully because I'm not the expert for WPS. We would need people like Benjamin Pross and others to explain that better.
See, I'm still a little bit confused about the differences between WPS and WCPS. Could you maybe kind of go over some more use cases about when you would use each of those processing specifications? I mean, I understand like WCPS. I mean, that's kind of like the more very powerful interface, right, and protocol, right, for doing these analytics and stuff. But do you have like some kind of like simple segregation between when you would want to use each one of those protocols specifications for accessing or science data? And doing
so as you're asking for use cases, use case is you have your own algorithm in mind. You have something that can be written down analytically as a request, then just throw it into the WCPS server, sorry, and you get back an answer. Use case for WPS would be, I have some mighty big code like climate simulation stuff, CFD code that I don't want to reformulate. I just want to use it over the web. Then you want to go for WPS, do a process definition, and then it's available on the web. If you want to have degrees of freedom, I want to ask any query anytime. Like you want to offer to your users the flexibility of doing all sorts of things which you don't even anticipate, then WCPS is the good means because it allows exactly that. Users can formulate what they want, and you do that in a safe way because you can control that. And by the way, our access control mechanisms also regulate how much data can you access, how much processing cycles can you spend, etc. So we can also protect that to make it secure. So do these use cases help somewhat?
Yeah, thanks for that clarification. That helps a lot. Thank you.
Okay, so as we are, well, pretty much now not at the end of ECP yet, but very soon, and this is our opportunity to sit together. Anything else you may want to give us on the way while we are defining OAPI coverages? Anything to discuss that we should look into? Anything that maybe you have ideas of what should be done, of functionality? Yes, please. Of course, after our meeting, you still could generate issues on the corresponding GitHub pages.
So I noticed the emphasis, of course, on spatial and temporal. What about other dimensions like spectral, for example? Is there a place for that in coverages?
Right. So actually, you have even strange cases because climate modelers like to have 2 time axes. So yes, that's possible. And then you can have other axes as well, like spectral, what you mentioned, or anything else. You just need to provide an axis definition. We need to be able to operate, to have the equivalent of regular and irregular, if that is wanted. And then you can compose your coordinate system definition, which maybe consists of latitude, longitude, and spectrum. So yes, that's flexible. And the subsetting mechanisms will work on that non-spatial temporal axis likewise.
So would output format be one of these axes, or it's kind of standalone?
Sorry, say again.
Like in one of your examples, you subset it by lat and long, but they also specified an output format.
Right.
And my question is, for things like output format and let's say output structure, things like that, is it defined as an axis as well, or is it pretty much like free form?
No, the output format is just the encoding. You get back a coverage, which is first of all an abstract concept, but then you need to nail it down to a string of bytes that can be sent over the networks. If you don't use an output format parameter, then you will get back the native format of the coverage as it is stored. So if you don't say anything and your coverage was netcdf on disk, you will get a netcdf response. Otherwise, you indicate your format, and if the server supports it, you will get it encoded. But there is this strict separation of the concepts, the functionality like axis, and the encoding. Does that answer your question?
Yeah, so isn't encoding a part of the standard, or is it something that
no, that's in the standard.
People define on their own.
That's in the standard.
Can you define like extra output controls, like output structure, or
okay, as per OGC,
grid?
You always can have vendor-specific parameters in addition, outside of the standard, which control extra behavior. So that is possible, but the standard does not foresee that you define your own parameters of the request. I guess implementers would kill us for that. Okay, last call. Any further comments, questions, complaints? Okay, hearing none, then thank you very much for bearing with me here. I enjoyed it very much having that session here. And you will enjoy lunch, I understand. So I want to keep you much longer. So thank you and enjoy your lunch. Bye-bye.